Maximum likelihood estimation for linear regression, a step-by-step derivation. Today, we derive maximum likelihood estimation for the linear regression model. Step by step. We begin with the model. Each outcome is written as a linear function of predictors, plus an error term. The key assumption is that these errors are independent and normally distributed, with mean zero and variance sigma squared. This means that, given the predictors, each observation follows a normal distribution centered around the regression line. The mean is x transpose beta, and the variance captures uncertainty around that line. Now we ask a different question. Given the data we observed, which parameter values make this data most likely? Because observations are independent, the likelihood is the product of individual densities. Each data point contributes one piece of evidence. Products are difficult to work with, so we take the natural logarithm. This transforms the product into a sum, making optimization tractable. After simplification, maximizing the likelihood is equivalent to minimizing the sum of squared residuals. We take the derivative with respect to beta, set it equal to 0, and solve the resulting equation. This leads to the familiar solution. Beta equals x transpose x inverse times x transpose y. We repeat the process for sigma squared. The result is the average of squared residuals, which measures how much the data deviates from the fitted line. With Gaussian errors, maximum likelihood estimation is identical to ordinary least squares. Maximum likelihood does not just give a solution, it provides a framework, linking models, data, and uncertainty into a single coherent approach.